Yeah, today this is my eighth session, eighth episode, and this particular episode is going to talk more from the optimization point of view, optimization procedures. As I told you in the beginning, I just gave a bit of information. I in fact touched most of the concepts in product design, and this was one of the concepts that I touched base, and this is optimization. And this particular session, I'm going to focus more on to optimization. In fact, this is going to be multidisciplinary optimization. See, optimization can be based on a certain product or a part, okay, or an assembly, etc. So that can be a geometrical optimization, or it can be a material optimization. Okay, it can be a process optimization also. So this is going to be more onto multidisciplinary optimization. So optimization from various aspects. So as a product, that complete product has got an optimization part. So this particular product has to be assessed from all possible directions. It can be from the geometrical aspect, it can be from the material aspect, it can also be from the process aspect. Okay, so from every aspect, we ensure that this particular product is going to be safer, durable, and sustainable. So that's the main intention behind multidisciplinary optimization. See, we generally term it as multidisciplinary optimization (MDO), or it is also called as multidisciplinary system design optimization (MSDO), or it is also called multidisciplinary design analysis and optimization. The reason because uh, this particular optimization takes care of product engineering, product analysis, product simulation, and it also takes care of the product manufacturing aspects. So everything under a simple, a single bracket called multidisciplinary optimization. So a small example I can give you here is early in 2008, I happened to be working on a project for one of the gas turbine gas turbine research establishments under the DRDO labs, and I was involved with one of the project directors, and this project director was taking care of various departments. So there was a department that was focusing on acoustics. There was a department that was focusing on thermodynamics, system analysis, as well as subsystem analysis, and there was a design that was focusing only on the product design part, and there was a department that was focusing on material science part. So this particular project director, Dr. Muralidharan, uh, once invited us, a team of our engineers, and put across a requirement, of gas turbine optimization. So this is in 2008 where they were working on one of the Pratt and Whitney uh, jet engines, that is gas turbines. And this particular project was going on for many long years, and this is at one of the specific time when there was a huge what do you call requirement of gas turbine that came into picture in the complete DRDO, where the DRDO had a time limit, and they were having a lot of pressure, immense pressure to develop the Tejas LC aircraft. So earlier they were working on few of the Russian made jet turbines, gas turbines, and they actually wanted to do a reverse engineering part. So, I mean, this is only for the study purpose, because based on this study is what they worked on the Kaveri engines, and this Kaveri engine initially became the industrial marine gas turbine, and then later on this particular engine was again extended for LC aircraft. So now this particular uh, gas turbine or the jet engine was dismantled, disassembled, and every part, they had studied, and they wanted to reverse engineer, a kind of reverse engineer, because this was a particular engine that was used for many, cycles. So, in fact, it has operated for about 10,000 or 20,000 or 25,000 hours. And what happens is the blades, the profile, the blade profile will start having a lot of changes. A lot of changes in the sense like there will be small changes, variations in the geometry, because these structures are supposed to be the critical structures in the overall design. And these structures, the geometrical design of these structures, the dimensions are very critical, that even the slightest variation can cause a lot of change in the efficiency. So it is the lift and drag coefficient. This lift and drag coefficient and the pressure ratio coefficient will make an immense change in the overall efficiency or the aerodynamics. So what they wanted to do is they wanted to make a reverse engineering, and they wanted to arrive at the suitable pressure ratio, the lift and drag coefficient, the suitable pressure ratio, and reconstruct the blades, the stator blades and the rotor blades, so that they will be able to get the best possible optimized or the most efficient aerodynamic parameters. Okay, so we had to start from a system uh, where physically the dimensions were extracted using the instruments, and these initial dimensions were extracted and the geometries were reconstructed, and most of the other critical components we had gone for rapid prototyping by 3D scanning and all this, and we reconstructed it from the cloud data. And once again, these CAD models, were reverse engineered, and there were some shape optimizations done. And then we had imported it to the CAE tools, and we did the pre-processing, and we ran the iterations, and then we found the results. So every component, every part were analyzed, the stability issues, the safety parameters, the deformation stresses, and all these things were studied. So this was the preliminary iteration. So now the complete set of parts, the assembly components were reversed, and we had done a lot of analysis. Now comes the actual scene where analyzing these components individually, these parts individually, okay, wasn't a problem, because we had done a lot of structural analysis, we had done a lot of dynamic simulations, we had also done flow dynamic simulations, aerodynamic simulations, external flow, internal flow, and individually all kinds of analysis were done, including the thermal, analysis. But what happens when all these analyses simultaneously act on this particular system? Say, for example, when the aircraft is in the flying mode, what happens is the gas turbines are under operating condition. The complete aerospace structure, the aircraft is subjected to thermal simulation. It is subjected to vibrations. It is subjected to acoustics. Okay, so a lot of these parameters comes into picture. Now, this complete optimization has to be performed. So that is multidisciplinary optimization. That is flow, acoustics, thermal, structural, etc. has to be simultaneously performed on this particular system, and then the optimization parameters have to be carried out. So this optimization, okay, is based on certain algorithms. So we have the mathematical formulations. Okay, it is almost like our statistical data. So we have Latin hypercube method, Monte Carlo method, and we also have specific other algorithms. Okay, that is suitable for distribution, probability distribution. We have a set of algorithms. So like that, we had certain softwares, and making use of these softwares, we try to perform the multidisciplinary optimization. And Optimus was supposed to be one of the MDO softwares that we were working with, and that's a French company. And this French company called Noesis is the innovator of this tool called multidisciplinary optimization tool called Optimus. And during my capacity as the product manager for the entire Asia Pacific on this particular tool, uh, I was representing the company. Okay, and we had been doing this particular benchmark for gas relevant research establishment, the DRDO agency, and there we had spent almost about close to 6 months. 6 months we had worked on that particular project, and we successfully, handed over the project, and we arrived at the most efficient blade profile, the aerofoil profiles, and we were happy to hand over the benchmark and successfully proven benchmark as well as the product that we developed called Optimus. So there are many, tools available today, and the most robust applications, okay, the most robust tools had all kinds of, formulations. So we also had something called genetic algorithm, and based on this genetic algorithm, we successfully created these aerofoils, and then we extracted the results, and we arrived at the best optimal structure. And this is one of the success stories that I am discussing about. Similarly, we have worked with a few automotive organizations also, wherein we had to optimize the A pillar and the B pillar for side impact and frontal impact and all those things. So this particular part of the design of experiments or the multidisciplinary optimization usually came on towards the crash analysis areas, that is the passive safety. So we are talking, whenever we talk about crash, it is passive safety. So which means we design the steering systems, the airbag simulation, airbag deployment, and the seatbelt constraints mechanisms. So we had worked on different thicknesses, we had worked on different fabrics, and the situations where two or more different parameters simultaneously changes, okay, those regions we go for multidisciplinary optimization. So this is not only restricted to aerospace and automotive. This finds immense applications in the oil and gas segments also, because there are more parameters which is simultaneously active. So what happens when there is a pressure drop, what happens when there is a pressure drop and a temperature increase, what happens when there is a pressure drop, temperature increase, and then atmospheric pressure variation. So, too many parameters, too many changes. Okay, we adopt this particular mechanism, or I mean, the process called multidisciplinary optimization. And this is a very important feature, especially for process integration. Say, for example, the oil and gas industry has too many processes, under that. Now, each process has got, each process has got a different execution style and different parameters. Now, let us imagine that there is a huge system, and that huge system has got about 15 to 20 subsystems, and each subsystem is operating in a separate process. So we will have about 20 processes, and one single complete system is going to be dependent on 20 different processes. So all these processes has to be integrated, and the design of the complete system has to be optimized. So in such criterions, we come for these kind of optimization. See, these are very complex in procedure, and where we have multi disciplines and tightly coupled what you call parameters, etc. And these parameters also influence each other. So, for example, let us take the aircraft wing. This aircraft wing is nothing but it's a continuous, the 0 to n integral section. So that is the complete aerofoil section of the wing at that particular length. Okay, so now each aerofoil has got a radius of curvature and different parameters in that. Okay, so now if there is a change in one single aerofoil, the entire aerodynamics changes. Okay, so which means one aerofoil to the other aerofoil section, the cross section thickness, it is coupled or it's it has got an influence. Okay, then we have simultaneous optimization. As I told you earlier, we have acoustics, we have thermal, we have structural, etc. And all these things have to be combined together. And based on that, there should be an optimization done. So this finds an immense application in such conditions. And we also have these applications, that is the multidisciplinary optimization applications in shipbuilding technology, naval architecture. Because like the aerospace industry, the aircraft, the complete fuselage system or the wing system, how the aerofoil is important, the design of aerofoil is important. Similarly, the ship also has got the sections, and each section is very important. Okay, especially in terms of hydrodynamics. Okay, so now when this particular structure is in motion, okay, there is going to be immense amount of loading acting on the structure, the ship structure. Okay, so there will be hydrodynamic forces, wave loads, okay, repetitive wave loads, and impact loadings, etc. Now, these many parameters have to be accounted for when we design the sections. Then we also have cooling systems for electronics. Then we also have the construction equipment. Construction equipments like your JCB, Hydra, escorts, etc. Okay, so there are too many parameters involved and too many iterations. Say, for example, there is a structure which is trying to remove earth, okay, from one area and it is going to dump it in the other area. So there are many possibilities. Okay, so now it is not only the bucket, it is also the boom, and it is also the arm, it is also the knuckle of that particular structure which matters. Now, what happens because of the earth pressure? Because of the earth pressure, there will be a huge amount of compressive load which is going to act on the bucket. And whatever compressive loads are acting on the bucket, there will be a tension load which comes, there is a tension load as well as the moment which is going to come onto the pinion mechanisms and also the knockers. And now what happens is there's going to be a tensile strength influenced, and this tensile strength which acts on the structure, it is going to again have a kind of compressive load which is coming onto the boom, and those compressive forces are going to again create a lot of moment, and that will create a torsion of the structure. So one load is more than sufficient to influence two or more different kinds of loading patterns on the structure, on a single structure. So in such critical cases, we make use of multidisciplinary optimization. And costing is very important. Computational cost mechanisms, analyzing and coordinating multidisciplinary multidisciplines. Okay. Now let me just give you a small example. Very recently, we faced the COVID-19 issue, and now there were people falling down in the sense like people every day there used to be about 100, 200, 275, 300 kind of people dying, and now it was unpredictable at some point of time because the rate of disease propagation and the rate of mortality, I mean the fatality occurring in one region, and the rate of men fatality and woman fatality, and similarly the kind of what do you call the time in which these fatalities used to happen. So there were too many parameters, and only based on these parameters they were able to find out, they were able to understand more about the kind of disease, the epidemic that has spread. And from these kind of statistical data or predictive analytics, AI based predictive analytics, because this is again an artificial intelligence, it's based on these predictive analytics, they were able to understand the disease, and they were able to generate a pattern out of it. And likewise, from the patterns whatever they generated, they were able to even understand what is the kind of suitable vaccination, or what is the kind of suitable antibiotic, or what is the kind of suitable medicine that will be able to take care of these particular fatalities. Okay, so there are immense applications that is going to influence. So different methods that I told you, because many uncertainties are there, and too many uncertainties, too many variables, too many parameters. Now all these things to be brought together and working on these parameters by keeping one fixed and the other varying, and the other fixed and the other one varying. So like that, too many uncertainties come into picture, and the duty, I mean the process is like to solve these uncertainties and arrive at the optimized figure. So we have decomposition methods. So these methods are to break down the complex multidisciplinary optimization problem into smaller or more manageable subproblems that can be solved. Example, the hierarchical or the non-hierarchical decomposition method. Then we have surrogation, that is the approximation methods. So where local minima, local maxima, we find out, and based on the uh, minima and the maxima, we try to go for some approximation. So approximation methods, we generally go for surrogation models and meta models, and based on that, we reduce the computational cost or analysis for creating approximations. Then we have optimization algorithms. So we have gradient based methods. So these are sequential quadratic programming. And then we have non-gradient based, which are genetic algorithms or particle swarm optimization, and usually used to find out the optimal solution within a defined problem space. So I gave you an example about the blade, the aerofoil optimization. Okay, so here in the aerofoil optimization, we use genetic algorithm. Okay, because uh, the parent structure has got an aerofoil, and the daughter section also has got the aerofoil, the same aerofoil. So the genera is the same. Okay, so what happens is all the parameters that the mother has, the characteristics, the same characteristics is shared by the daughter also. Okay, so that is the reason we call it as genetic algorithm. And then we also try to, uh, you know, uh, uh, do a lot of what do you call process optimizations. As I told you in the oil and gas segment, there are too many procedures. Downstream, then you have the midstream, and then you have the upstream. Now, there are a number of processes in the downstream. There are a good amount of processes happening in the midstream, and there are good amount of processes which is happening in the upstream. So these many procedures have to be iterated, and it's not only one or two iterations. There are hundreds and hundreds of iterations happening, and based on these iterations, okay, it's a neural network, it's basically a neural network. Okay, so now based on this, the best possible output has to be generated, because time savings is very important, cost savings is very important. Okay, and apart from time and cost, there are people resources, people cost involved, the resource cost involved. So all these overhead costs, the total cost, and everything is dependent on the processes. The bigger the process, the bigger the the time consumption, the bigger the cost also involved. Okay, so let me just try to do a small revision here, like whatever we discussed about how better or how important optimization, is in terms of product design, and how important is this optimization in the most successful and the most sustainable product, and what are the kinds of optimizations that we generally adopt, and how these optimization procedures are used in all kinds of industry verticals, and this is supposed to be one of the most important processes in the product design industry. So I would again request you to kindly subscribe to this particular video and share this video to as many people as possible. The reason because this is one particular topic in the entire engineering where people really don't understand like what exactly is optimization and how is optimization done. It is not only about the geometrical optimization, doing fiddling with the dimensions, the length, the width, the breadth, the radius, etc. It is not only fiddling with the geometrical design. It is as equally important as fiddling with the processes involved, and two or more different physics combined together. That is multi-physics. Okay, the optimization of multi-physics. So that is what we mean by multidisciplinary optimization, and this is a very very important part. Until you exactly understand what is this particular process, you will never be able to perform a optimization. See, no matter what the kind of tools you are using, okay, it is not only about the tool, it is about the decision making. You need to understand the problem, and based on that problem you need to arrive at the right algorithm, whether it is going to be a decomposition method, whether it is going to be a neural network GNN method, that is a genetic algorithm method, or whether it is going to be just a simple statistical method. You need to understand the problem, and based on that particular problem, you need to apply the algorithm, and that is when you arrive at the right optimization procedure. So let me uh, wind up today's session, and I would like everybody to subscribe to this channel so that you will be able to see all important and interesting videos. And there are several videos in the stack which you will be able to only access once you have subscribed to this particular channel. Okay, so kindly send your valuable feedbacks and comments so that I will be able to make a separate session or a video based on that, and I can also ensure that there are some specific case studies taken, and then we work on those case studies also. Okay, I don't want to make this a completely, a numerical session or a mathematical session, because there is then definitely there is no difference between what exactly happens in the book and what happens here. Here it's going to be a more of interactive session where I want you to understand the practical problems, and I want you to understand what would be the most feasible solution for that. Okay, so anyway, thank you. Have a wonderful time. Okay, please subscribe and share this. Okay, thank you.